In the deepest, most silent auditorium of the cosmos, where the only light is the ghost of creation itself, a story is being told. It is a story that unfolds not in words, but in the faint, stretched whispers of ancient photons, travelers who have journeyed for over 13 billion years to reach us. They carry with them a vision of the cosmic dawn, a time when the universe was a blank canvas, shrouded in a pervasive dark. Out of this primordial silence, the first lights began to flicker, not with a sudden roar, but as hesitant, scattered embers in an infinite night. These were the first stars, the first galaxies, fragile islands of order in an ocean of expanding chaos. For decades, we have peered into this abyss, using our greatest telescopes as time machines, seeking to witness the universe's infancy. And with the golden eye of the James Webb Space Telescope, we have finally parted the veil. We expected to find nurseries of young stars and the faint outlines of adolescent galaxies. But we found something else. Something impossible. Hiding in plain sight, a mere 570 million years after the Big Bang, we found a monster. It is a black hole, catalogued as CEERS 746, and it is a temporal paradox, a creature of staggering mass that, according to our most trusted cosmic timelines, simply should not exist. It is 10 million times the mass of our Sun, a supermassive being in a cosmic era that should have only hosted infants. It is like finding a titan in a nursery of newborns. Its presence breaks our models of cosmic evolution, shattering our understanding of how these gravitational leviathans are born and how they grow. How could such a singularity, a being of such profound density and appetite, have assembled itself so quickly in a universe that had barely learned how to build stars, let alone devour them? This is not just a question of astronomy, it is a question of origins. It challenges the very story we tell ourselves about the universe, from its first breath to the grand structures we see today. Tonight, we journey back to that dawn. We will stand at the edge of cosmic morning and confront this beautiful, terrifying anomaly. We will explore the lives and deaths of colossal stars, the violent cradles of the first galaxies, and the exotic theories that scientists have conjured to explain the inexplicable. We will seek to understand how the universe, in its youth, could have forged a monster. Are you ready to look into the abyss and see what looks back? Now, let's begin. Music. To comprehend the sheer impossibility of CEERS 746, we must first understand the accepted, elegant, and profoundly gradual way the universe was thought to build its giants. The story, as we knew it, begins with a single, magnificent star. Imagine a star unlike any our modern galaxy knows, a population 3 star, born from the pure, unblemished hydrogen and helium forged in the Big Bang's crucible. It is a star of unimaginable scale, hundreds of times the mass of our own Sun, burning with a fierce, blue-white intensity that is almost blindingly pure. Its life is not a gentle, billion-year simmer like that of our star, but a violent, million-year explosion. It lives fast and dies young. In its core, the furnace of nuclear fusion rages with an intensity that strains the very limits of physics. It converts hydrogen into helium, then helium into carbon, oxygen, and heavier elements, seeding the cosmos with the building blocks of future worlds and future life. But this act of creation is also an act of self-destruction. The outward pressure of its radiation, a gale of light pushing against its own immense gravity, is a battle fought on an epic scale. For a few million years, a tense equilibrium holds. The star breathes, a colossal lung of plasma expanding and contracting, its surface churning with solar flares the size of entire solar systems. It is a king, ruling its small patch of the dark, but its reign is destined to be brief. The fuel in its core is finite. As the fusion engine stutters, climbing the ladder of elements until it forges iron, it reaches a dead end. Iron is cosmic ash, fusing it consumes energy rather than releasing it. The star's furnace goes out. In an instant, the delicate balance is broken. Gravity, the patient, relentless force that has been trying to crush the star its entire life, finally wins. The victory is absolute and catastrophic. The outer layers of the star, no longer supported by the pressure from below, begin to fall inward. They accelerate to a quarter of the speed of light, crashing down upon the impossibly dense core. The result is a rebound shockwave of unimaginable power, a core collapse supernova. The star detonates, tearing itself apart in a blast that can outshine its entire host galaxy for a few brilliant weeks. In this final, glorious act, it scatters the elements it forged across space, enriching the void. But at the heart of this expanding nebula of gas and dust, something remains. The core, too massive for any force in the universe to halt its collapse, continues to fall inward. It crushes itself past the point of neutron degeneracy, the last standpoint of matter as we know it. It collapses into an object of zero volume and infinite density. A stellar mass black hole is born. It is a shadow, a wound in space-time, typically only 10 to 20 times the mass of our Sun. It is a seed of darkness, but it is just that, a seed. It is not a monster. It is an infant, and for it to grow into the supermassive titan we see at the heart of galaxies like our own Milky Way, it must feed. And it must have time. Billions and billions of years of time. This was the story we told, the only story that made sense. And it is this very story that CEERS 746 renders obsolete. The birth of a stellar mass black hole is not an ending, but the beginning of a second, far longer life, a life of consumption. This newborn singularity, this ghost of a dead star, now possesses the most powerful tool in the cosmos, its own profound gravity. It is an invisible hunger, warping the fabric of space-time around it, creating a well from which nothing, not even light, can escape once it crosses the event horizon. In the chaotic aftermath of the supernova that birthed it, or later as it drifts through the dense gas clouds of its nascent galaxy, it begins to feed. Gas, dust, asteroids, and even unlucky stars that wander too close are caught in its inexorable grip. They do not fall straight in. Instead, they are pulled into a swirling, incandescent vortex known as an accretion disk. Here, matter is accelerated to near the speed of light, its constituent atoms torn apart by ferocious tidal forces and friction. This cosmic grinding wheel heats up to millions of degrees, glowing more brightly than a billion stars combined. This is the paradox of a black hole. The darkest object in the universe is surrounded by the brightest phenomenon imaginable. It is this light, the dying scream of matter, that allows us to see them at all. But this very brilliance is also the black hole's biggest constraint. The intense radiation blasting out from the accretion disk exerts a powerful outward pressure. It is a wind of pure light, pushing back against the very gas and dust that is trying to fall in. This cosmic balancing act is known as the Eddington limit. It is a fundamental speed limit on growth, a natural governor that prevents a black hole from eating too quickly. If it tries to pull in matter too fast, the resulting radiation becomes so intense that it blows away its own food source, effectively starving itself. A black hole can only consume so much, so fast, without choking. And this is the crux of the problem. Even if a stellar mass black hole, born from the first generation of stars, were to feed continuously at the absolute maximum rate allowed by the Eddington limit, without interruption, for every single moment of its existence, the mathematics simply does not work. To grow from a starting mass of, say, 20 suns to the 10 million solar masses of CEERS 746 would require far more time than the universe had to offer just 570 million years after the Big Bang. It's like asking a single bacterium to consume an entire whale in under a minute. The physics of consumption, as we understood them, forbade it. Something had to be wrong. Either our understanding of the Eddington limit was flawed, and black holes had a way to binge eat in what is called super-Eddington accretion, or the initial seed wasn't a seed at all. Perhaps it wasn't born from a single star. Perhaps the universe, in its chaotic youth, had a different, more direct, and far more terrifying way of creating its monsters from the very beginning. The neat, tidy story of stellar collapse was not enough. The evidence demanded a more radical origin story, one born not in the heart of a dying star, but in the heart of a collapsing cosmos. Let us pull our focus back, away from the singular fate of one star, and gaze upon the wider environment of the cosmic dawn. The universe, less than a few 100 million years old, is a place of profound emptiness and staggering potential. It is not the structured, orderly cosmos we know today, with its well-defined spiral and elliptical galaxies. It is a turbulent, primordial soup. The vast majority of the universe is a diffuse, cooling fog of neutral hydrogen and helium, threaded with the invisible scaffolding of dark matter. Gravity is slowly, patiently at work, pulling this primordial gas into the deepest wells of the dark matter web. In these dense knots, the first structures are beginning to form. They are not yet galaxies, but protogalaxies, clumsy, chaotic, and small. They are fragile collections of gas, perhaps only 1,000,000 times the mass of our Sun, 1,000 times smaller than the modern Milky Way. Within these gaseous halos, the conditions are finally right for the first stars to ignite. These are the legendary population 3 stars, the true giants of creation. Forged from gas untouched by the heavy elements of previous stellar generations, they are free to grow to colossal sizes, hundreds, perhaps even 1,000 times the mass of our Sun. They blaze into existence, searing the surrounding darkness with ultraviolet light. Their birth is a pivotal moment. Their radiation begins to ionize the neutral hydrogen fog that surrounds them, like cosmic lighthouses burning away the mist. This is the epoch of reionization, the moment the universe truly became transparent and filled with light. But these stars are also agents of chaos. Their powerful stellar winds and the eventual supernova explosions that mark their deaths are violent events. They churn the gas within their host protogalaxies, heating it and blowing it outwards. This feedback can be so intense that it temporarily halts further star formation, regulating the growth of these early structures. The early universe is a battlefield of opposing forces, gravity pulling matter together, and the radiation from the first stars pushing it apart. It is a delicate, violent dance that dictates the pace of cosmic evolution. It was within this specific, unique environment, an environment of pure, primordial gas and intense, nearby radiation, that a new, more exotic possibility for monster making could arise. The standard path required a star to form, live, die, and then for its remnant to grow. But what if the universe could skip a step? What if, under just the right conditions, you could bypass the star formation process entirely and create a giant from the get-go? The stage was set for a different kind of collapse, one not of a stellar core, but of an entire cosmic cloud. In the churning heart of a protogalaxy, a colossal cloud of primordial hydrogen and helium begins to feel the inexorable pull of its own gravity. This cloud is immense, containing the mass of 100,000 suns. Under normal circumstances, as such a cloud contracts, it would cool and fragment into thousands of smaller clumps, each one destined to become an individual star, forming a dense star cluster. This is the standard, democratic process of star formation. But here, in this specific corner of the early universe, something is different. The cloud is being bathed in a torrent of intense ultraviolet radiation, but not from within. The light comes from a neighboring protogalaxy, close enough to irradiate the cloud but far enough away that its gravity doesn't tear it apart. This external radiation acts as a blanket, keeping the gas warm. It prevents the hydrogen atoms from pairing up into hydrogen molecules, the key cooling agent that allows a gas cloud to fragment. The cloud remains hot, and because it cannot cool efficiently, it cannot break apart. It is trapped. It continues to collapse under its own weight, but it does so as a single, monolithic entity. The entire mass of 100,000 suns, a mass that should have given birth to a generation of stars, is now falling inward toward a single point. As it collapses, it forms a massive, supergiant protostar at its center, a temporary object bloated to an incredible size, perhaps as large as our entire solar system. But it is too massive to find stability. Its core temperature and pressure skyrocket to levels that even a population 3 star could never achieve. The collapse becomes relativistic and unstoppable. The entire cloud, in a process taking perhaps only a few 100,000 years, does not form a star cluster. It does not detonate in a supernova. It collapses directly into a black hole. This is the direct collapse black hole model. It is a shortcut. It is the universe's secret recipe for creating monsters in a hurry. The resulting object is not a stellar mass black hole of 10 or 20 solar masses. It is an intermediate mass black hole, born with a staggering mass of tens of thousands, or even 100,000, suns. It is not an infant seed. It is a giant, born fully formed from the substance of the cosmos itself. It is a heavy seed, a gravitational anchor dropped into the heart of a young galaxy ready to command and consume from its very first moment. This theory, once considered a fringe idea, now stands as one of the most compelling explanations for the existence of early quasars and behemoths like CEERS 746. It paints a picture of a universe more clever and more violent than we ever imagined, with more than one path to create its shadows. The birth of a direct collapse black hole is a transformative event for its host galaxy. Unlike the remnant of a single star, which might drift through its galaxy for millions of years before finding the dense central regions, this heavy seed is born right where it needs to be, at the gravitational heart of the protogalaxy. It is the anchor from which everything else will grow. The galaxy in which CEERS 746 resides, a small but actively star-forming disk galaxy catalogued as CEERS 1019, now has a central engine of immense power. This black hole, born with a mass of perhaps 100,000 suns, immediately begins to shape its environment. Its gravitational influence is profound. It stabilizes the orbits of gas and stars, creating a more orderly structure than the chaotic clumps that characterized the earliest protogalaxies. It provides a central point for gas to flow toward, funneling a steady stream of fuel into its waiting accretion disk. Now, the Eddington limit is still a factor. The black hole cannot consume with absolute abandon. But its massive head start changes the equation entirely. Growing from 100,000 solar masses to 10 million is a far, far easier task than growing from 20. The timeline suddenly becomes plausible. The monster is no longer an impossibility, but an inevitability. We can imagine this young system, CEERS 1019, coming alive. At its heart, the quasar powered by the direct collapse seed flares into existence, a beacon of ferocious light visible across the cosmos. This light is a double-edged sword. It pushes gas away, but it also triggers compression fronts in the surrounding medium, sparking new waves of star formation in the galactic disk. The galaxy and its central black hole enter into a symbiotic, co-evolutionary dance. The galaxy provides the fuel for the black hole to grow, and the black hole, through its energetic feedback, regulates the galaxy's own growth, preventing it from forming stars too quickly and blowing itself apart. This relationship, this feedback loop between a supermassive black hole and its host galaxy, is a cornerstone of modern astrophysics. We see it everywhere in the local universe. But CEERS 746 and its host galaxy show us this process happening in its infancy, just a few 100 million years after the Big Bang. We are witnessing the very beginnings of galactic architecture, with a heavy seed black hole acting as the chief architect. The galaxy, CEERS 1019, is not just a home for the black hole, it is its creation, its body. The stars that form in its disk are children of the same primordial gas cloud that fed the central monster, forever bound to it by gravity. The light from the quasar illuminates a system in the throes of its own becoming, a place where the rules of creation were being written, and where the universe proved it could build its grandest structures with breathtaking speed. The direct collapse model is elegant and powerful, but it requires a very specific, almost pristine set of cosmic circumstances, a massive, primordial gas cloud irradiated by a precisely distant neighbor. Such Goldilocks conditions may have been rare, even in the early universe. And so, cosmologists have another card up their sleeve, another pathway to a heavy seed that is perhaps even more brutal and chaotic. This story does not begin in a quiet, irradiated cloud, but in the most violent and crowded places in the early universe, a dense, young star cluster. Imagine, once again, a protogalaxy forming. But this time, the gas cloud is allowed to cool and fragment. It gives birth to not one entity, but thousands of population 3 stars, all packed together in a gravitationally bound cluster no more than a few light-years across. This is a cosmic mosh pit. The stars are so close together that their gravitational interactions are constant and violent. They swing past each other in frantic, looping orbits. The most massive stars, through a process called dynamical friction, lose orbital energy and sink toward the center of the cluster, like heavy stones in a shaken box. Within a million years, the core of this cluster becomes a churning cauldron of stellar behemoths. Their lives are short. One by one, they exhaust their fuel and collapse, not into supernovas that would blow the cluster apart, but directly into black holes, swallowing their own explosions. Now the core is populated by a handful of stellar mass black holes, each 10 to 20 times the mass of the Sun. they too sink to the absolute center. What happens next is a gravitational battle royal. These black holes begin to merge, releasing tremendous bursts of gravitational waves. But they also begin to consume their neighbors. A star that wanders too close is torn apart in a tidal disruption event, its gas feeding the growing black hole. More dramatically, in such a crowded environment, direct physical collisions are possible. A black hole might swallow a massive star whole. The central black hole grows, and as it grows, its gravitational cross-section increases, making it an even more effective predator. It enters a state of runaway growth. It cannibalizes its sibling black holes. It devours the most massive stars in the cluster. It undergoes a series of rapid mergers and collisions, its mass doubling and redoubling in a cosmic feeding frenzy. In a few million years, this process of runaway collision could transform a collection of 10 solar mass black holes into a single intermediate mass black hole of thousands of solar masses. This seed, forged in the heart of a dense stellar crucible, is then a viable candidate to explain the rapid growth of a quasar like CEERS 746. It has the necessary head start. Eventually, this dense cluster, now anchored by its new central monster, would merge with other clusters and gas clouds, forming the nucleus of a larger galaxy, with the heavy seed already in place. This is the universe as a demolition derby, building its giants not through gentle collapse, but through relentless, brutal cannibalism. We are now faced with two compelling, yet starkly different, narratives for the origin of a heavy seed black hole. The first, direct collapse, is a story of cosmic monoliths, a single, massive cloud collapsing under specific, almost sterile conditions. It is a process of immaculate conception on a galactic scale. The second, runaway mergers in dense clusters, is a story of chaotic, violent assembly, a messy, crowded, cannibalistic free-for-all. It is a process of growth through conquest. Which of these pathways is the more likely origin for CEERS 746? The data from the James Webb Space Telescope provides tantalizing clues. The host galaxy, CEERS 1019, is observed to be a relatively ordered, disk-like structure, even at this early epoch. It is not a messy, irregular clump. This observation might lend weight to the direct collapse model. In this scenario, the heavy seed forms first, at the center of a large, rotating gas cloud. The rest of the gas settles into a stable, rotating disk around this pre-existing gravitational anchor. The galaxy essentially grows its disk around the black hole, leading to the orderly structure we see. The runaway merger model, by contrast, might be expected to produce a more chaotic environment. The process of forming a dense star cluster and the subsequent violent mergers would churn the surrounding gas and stars, likely resulting in a more spheroidal or irregular bulge component at the galaxy's center, rather than a clean disk. The apparent lack of a significant central bulge in CEERS 1019 is a point in favor of direct collapse. However, the universe is rarely so simple. It is entirely possible that the runaway merger process occurred, and the resulting intermediate mass black hole later captured a large stream of cold gas, which then settled into the disk we observe today. The initial chaos could have been smoothed over by subsequent evolution. Furthermore, the conditions for direct collapse are so specific that they may have been exceedingly rare, while dense star clusters were likely a common feature of the early universe. Perhaps both mechanisms were at play, creating a diverse population of black hole seeds with different masses and in different environments. CEERS 746 might be an example of one path, while other early quasars discovered by Webb might be examples of another. This is the frontier of modern cosmology. We are no longer asking if heavy seeds existed. The discovery of objects like CEERS 746 has elevated that from a theory to a near certainty. The question now is how? By what precise mechanism did the infant universe have the capacity to forge these giants? Each new observation from Webb, each new spectrum of an ancient galaxy, provides another piece of the puzzle. We are like cosmic detectives, examining the scene of a 13-billion-year-old event, weighing the evidence for two different suspects, each with a credible motive and method. The final verdict is not yet in, but the investigation has revealed a universe far more dynamic and creative in its methods of creation than we ever dared to imagine. All of this knowledge, this entire cosmic detective story, is made possible by the photons. They are the messengers. For 13,290,000,000 years, a stream of light particles has been traveling from the accretion disk of CEERS 746, aimed at a patch of space that would, one day, hold our planet. They began their journey when the universe was a fraction of its current size, a mere toddler. As they traveled, the universe itself expanded beneath them, stretching their wavelengths, redshifting their light from a brilliant, searing ultraviolet to a faint, cool infrared. They journeyed through the epoch of reionization, past the formation of the first large galaxies, past the swirling nurseries of stars that would form the Milky Way. They flew past the location where our Sun and Earth would eventually condense from a cloud of interstellar dust, billions of years before that event even occurred. They are time capsules, each photon carrying an imprint of the conditions in which it was born, the temperature of the accretion disk, the chemical composition of the gas, the velocity of its swirl. For millennia, these photons rained down on Earth, unseen, their message lost to the opacity of our atmosphere. Then, we built an eye. A golden eye, comprised of 18 hexagonal mirrors, cooled to within a few degrees of absolute zero, and placed 1,000,000 miles from Earth, beyond the obscuring glow of our own world. The James Webb Space Telescope. After its long journey, one of these ancient photons, a survivor of an odyssey across space-time, finally ends its flight. It strikes one of Webb's mirrors, is focused through a series of optics, and is directed into an instrument called a spectrograph. This instrument does what our eyes cannot. It splits the faint infrared light into its constituent colors, a rainbow of the abyss. In this spectrum, astronomers read the story. They see the broad emission lines characteristic of hot gas swirling at incredible speeds around a massive object, allowing them to calculate the black hole's mass. They measure the precise amount the light has been redshifted, telling them exactly how far away, and therefore how far back in time, they are looking. They see the signatures of different elements, probing the nature of the gas that fueled this ancient engine. JWST is not merely a telescope, it is a time-traveling laboratory. It allows us to perform forensics on a cosmic scale, to analyze the evidence left behind by events that transpired when the universe was in its infancy. The discovery of CEERS 746 was not a single eureka moment, but the painstaking result of collecting these faint messengers, decoding their stretched-out language, and piecing together a picture that defied expectation. It is a testament to human curiosity, the drive to build a machine capable of catching the whispers of creation itself, and in doing so, to confront the beautiful, humbling fact that our story of the cosmos was incomplete. The photons delivered their paradox, and in doing so, handed us a new chapter of cosmic history. We began our journey with a paradox, a monster in the nursery of the cosmos. A black hole so massive, so early, that it seemed to mock our established timelines of cosmic growth. We journeyed through the life and death of the first stars, witnessing the birth of stellar mass black holes, and saw why this standard model was not enough. The speed limit of growth, the Eddington limit, stood as a firm barrier, making the existence of CEERS 746 a mathematical impossibility under the old rules. This forced us to seek more exotic, more radical origins. We explored the possibility of direct collapse, where a colossal cloud of primordial gas, under very specific conditions, could bypass the stellar phase and fall directly into a heavy-seed black hole. And we explored the brutal alternative, a runaway series of mergers and cannibalism within the violent heart of a dense star cluster. The mystery of CEERS 746 is, in a sense, resolved. It is no longer an impossibility, but a profound piece of evidence. Its existence confirms that the early universe did indeed have mechanisms for creating these heavy seeds. The debate is no longer if, but how. Whether by monolithic collapse or by chaotic assembly, the universe was capable of jump-starting the growth of its supermassive black holes, forging the anchors around which the first galaxies would be built. The story of CEERS 746 is not just about a black hole. It is about the co-evolution of darkness and light. These early giants were not merely agents of destruction. They were the gravitational architects of the cosmos. Their immense gravity organized the chaos of the early universe, providing the scaffolding for galactic disks. Their radiative feedback, the light from their accretion disks, regulated star formation, ensuring galaxies grew in a sustainable way. They were the beating hearts of the first great cosmic cities, their violent hunger inextricably linked to the creation of the stars and structures that surround them. We look out at the grand tapestry of galaxies today, including our own Milky Way, and we see that every large galaxy has a supermassive black hole at its center. This was once a puzzle. Now, thanks to the light from objects like CEERS 746, we see that it may have been the defining principle of their formation all along. The black hole did not come later; in many cases, it may have come first, the seed from which the entire galactic garden grew. We have peered back to the dawn, and found not an empty stage, but a universe already busy building its most monumental structures with a speed and violence we are only just beginning to comprehend. The story of the cosmos is grander, stranger, and more magnificent than we knew. And now, as you close your eyes, imagine that ancient light, that whisper from the dawn. Imagine the silent, awesome power of 100,000 suns collapsing into a single point, a seed of gravity that would anchor a galaxy for billions of years. What would you have done if you could witness it?